first like to thank the Physical Oceanography Lab for the great food. Dr. Qing Wang is a professor of meteorology at the Naval Postgraduate School in Monterey and is also affiliated research faculty here at Moss Landing Marine Laboratories. She's an expert in electromagnetic ducting and the air-sea interface, study of light and radio waves are bent and distorted, forming mirages and radar distortion along the horizon. Her studies employ instrumentation to measure heat and water vapor flux, marine aerosol composition, atmospheric water droplet inventory, and optical infrared X-band radio distortion. She earned a BS and MS degree from Peking University and a PhD from Penn State University. And before coming to Monterey, she completed a 2-year postdoc at the National Center for Atmospheric Research. She's currently directing several multidisciplinary and multi-institutional programs nationwide and is working with Kenneth Cole and the Chemical Oceanography Lab regarding the role of fog in the transport of contaminants from the sea to the land. Most recently, this involves investigating the Santa Ana winds off Point Magoo using Moss Landing Marine Labs vessels and with ML students. She's an accomplished researcher and an internationally respected researcher, so let's give her a warm welcome.
Thank you, Tom, for the introduction, and thanks for inviting me. It's a pleasure to be here, and thanks everybody. You know, this Thursday afternoon at 4 o'clock, but I guess there's food. So talking about the recent field project, and actually it's called Santa Ana Study Project, and we just wrapped it up 2 days ago. And actually, JD, I think, is still there in Moss Landing, if not transiting back. So that's very, very recent. Now, so I want to take this opportunity to introduce, in a general sense, my research area. So it's not just a name, so you actually know what I'm doing. And so I understand, most of you do not have the meteorology background, so I'm getting to some of the basics. So my research area is kind of broad and has been expanding forever. So I'll try to stay focused with my recent projects. So here I'm talking about the keywords here you see is air-sea interaction, and in the eyes of boundary layer meteorologists, that's what I label myself. So when people know I'm a meteorologist, they will ask, "Oh, what's the weather for tomorrow?" And I said, "Well, check the website," because I'm a physical meteorologist, and I'm even more, I'm a boundary layer meteorologist. So what exactly is the boundary layer? And so that's something I will talk about. Now here I will introduce introduction to the atmospheric boundary layer. What are we talking about? And what are the processes, the physical processes that we are interested at the air-sea interface? And then I will talk a little bit about boundary low-level cloud and the fog. And this is where Kenneth and I identified our common interest. And then I will talk about my recent program, CASPER, and environmental effects on the electromagnetic wave propagation, basically radar propagation in the radio wave range. And then I will introduce quickly about the atmospheric effects on the optical system, and particularly high energy laser. This is the new project that I was just notified like 2 weeks ago. I'm funded a 5-year project. And so I will talk about what are we trying to accomplish? What are we dealing with in this boundary layer? And then the importance of boundary measurement and what we do with the measurement and how we design the data collection process. And sometimes we work with new ships that new to us, or so they feel what we are doing are really bizarre. It's not the normal, doing CTD cast, and so they'll say, "What? You want to do a balloon on a small ship?" So we're doing some strange things, but it's all fun. And so Alex can tell you. And finally, I'll give a summary. So now, what is the boundary layer? So the atmosphere okay, and invisible, but we can separate it into many layers, okay? And this lowest deep layer is what we call the troposphere, and many of you know. Now, the boundary layer is the lowest 1 kilometer of that troposphere, and its basic major characteristic is in direct contact with the surface, and as a result, is turbulent. So, if we look into a layer and we see it's not turbulent, and then that's not the boundary layer of the Earth system. Okay, so that's the major characteristics of the boundary layer is turbulence. So now the formal definition of the boundary layer is it's directly affected by the surface, and also it responds to the surface within an hour. So there's I'm sorry, I forgot to. Let me just.
If that's for me, you just tell them I'm busy right now.
I'll just put it to. Okay, so that's the directly affected by the surface and responds to the surface forcing within an hour. This time scale is very important because eventually everything in the upper atmosphere is going to feel the effect of the surface and the ocean. Okay, it's just a matter of how long. Now, in the boundary layer, you feel it right away, basically. Okay, so that's where it makes a difference between the boundary layer. Now, in the boundary layer here, and normally we have something at the very top. This has to, we call the temperature inversion. This is, temperature normally decrease with height, but in this layer, it's increasing with height. So we call it a temperature inversion. And accompanied with that, and we have the water vapor decreasing with height. So it's getting drier above. And this is particularly true, of course, over the ocean because we have a big source of water here, okay? And within this layer, and then we also separate it into, this part is called the surface layer, which is really direct in contact with the surface, and it really feels what's going on in the surface. And this is normally like 10% of the entire boundary layer. So if we do the math, 1 kilometer is the normal height of the boundary layer, 10% of that is about 100 meters. So we're talking about this lowest layer is 100 meters. Now, what you see here in this lowest layer, water vapor, we have a strong gradient, so I think this labeled wrong. Hold on. Q is, so this should be Q, and this should be temperature. So anyway, in this layer, and we see the strong gradient. Okay, it varies with height significantly, and lots of times it's the vertical variation that we are interested at as boundary meteorologists. So now, what's going on in this boundary layer? As a result, it's responding to the surface quickly. So we see the strong diurnal variation. So during the day when the sun rises, and then that's when we have, the boundary layer will evolve. You heat up the surface, and then you get lots of mixing and turbulence. And then at night, and the surface cools, and you develop a different type of boundary layer. So we have this very strong diurnal variation, and at the sunrise and the sunset, and then we are going to see very strong, very quick development of the boundary layer. Now, this is not completely true over the ocean because the ocean surface do not have such a significant diurnal variation, but over the ocean we do have some diurnal variation in the sea surface temperature, and it's just not as dramatic as over land. Now, this is from my measurement with the tether balloon over Kansas, so you can see, this is during the day, the temperature goes like this, and then right at sunset, and then now you start to see this development of the stable boundary layer because the surface is cooling very rapidly. So the temperature is cooling off very rapidly. So that shows, the response of this boundary layer to the surface forcing. Now, so near the ocean surface, and what's going on? Oops, wrong button. Okay, so now these are the processes we're looking at, the physics involved. Okay, and of course in the upper ocean we have the circulations and we have the Ackermann transport gradient, and there's waves and all that. And then at the bottom there's the bottom effect. So so Tom is an expert in that. Now this is my territory when it comes to here. And so now at this interface, now we have the wind. And then now this wind, so this is the forcing from the atmosphere to the ocean. And as a result of that, it generates this momentum mixing. So that takes care of the momentum transport between the atmosphere and the ocean. And that's this surface stress part. Okay. And then we have also, because there is an air and sea temperature difference, so you are going to have the sensible heat, transporting either way. It can be plus or minus, because when the ocean is warm and the air is cold, so you have the heat coming from the ocean. And when the ocean is cold, atmosphere is warmer, and then you have the heat going into the ocean. So that's a two-way traffic. Now, then when we get into the evaporation part, and this is most of the time is a one-way traffic, the surface is evaporation. So you have water vapor into the atmosphere. This is extremely important to atmosphere, especially to the, especially when we are talking about hurricanes, for example, because the precipitation and the rain development, it depends on these water vapor. So the different ways you can model this, and then that's going to change the intensity and also the track of the hurricane. So and this accompanied with this evaporation, in addition to the water vapor input into the atmosphere, and we also have the heat. Because when you evaporate, you need heat. That's the so-called latent heat flux. Okay? So now I have all these three are circled in this, and these are the ones we have been trying to measure. So when you see those sound anemometers we put on the John Martin, and we put some Lycor to measure the fast water vapor, and those are really for measuring these three quantities. Now, why are they important? Okay, now when we talk about how the atmosphere and ocean are coupled, and these are the couplers. Okay, so these are the mechanisms. Then the ocean and the atmosphere exchange momentum and sensible heat energy and the latent heat energy and mass of the water vapor. And some other people are interested in the CO2, and that's in the form of the flux, from the ocean as well. So I always measure CO2 because that's come with the sensor, but I have no idea how to explain them. So if you ever need CO2 data, I have lots of them, just I don't know what to do with them. Okay. So that's the ocean, the air-sea interface, the processes. And so in the forecast model, okay, these are the three. So the forecast model need from boundary meteorologists like me. Okay? And so they want to be as faithful as to the true atmosphere as possible. That's what we call the surface layer surface flux parameterization. Okay? So now this parameterization is an issue because there's a scale mismatch, because these things happen at very small scale. So we're talking about millimeter, centimeter to meter and kilometer. Okay. Now, so the forecast model, and they cover the fine resolution, and we're talking about 3 kilometer, operational forecast, 5 kilometer. So all these processes are the so-called subgrade scale. Okay. So the forecasts are on this scale, but the processes we're looking at on this scale. So we somehow need to make the connection between what's going on here to what's being forecasted. Okay, so that's the flux parameterization, and that's where lots of the research has been done, about the surface flux parameterization. Okay, so now when we get to the upper boundary layer, okay, and then we get into the so-called turbulence transport, and sometimes we have this layer of cloud. Now, when this layered cloud, when it gets really low, get down to the surface, and that becomes, what we know as fog. And we are particularly interested in these, because we have lots of these, on the West Coast, and particularly in the summer period. Now, what happens here, during that period, the larger atmosphere has this large-scale slowly descent, so it's just pushing the air, slowly. And then, but you don't see the atmosphere is being crushed to the surface because there's something going on in the atmosphere. Now, what's going on here now? It's if you have a warm ocean surface and it's going to give some buoyancy, you generate turbulent mixing, so that's mixing going on. Now, if you don't have those, so normally what we have here, the ocean surface are pretty cool. Now, but we have this cloud. Now, what happens here is the cloud, everything is emitting infrared radiation. So you, the chair, the table, everything. Now, the cloud is emitting to the space, and at the same time, it's receiving emission from the air. But the amount cloud emit is a lot more than what they can receive from the air. So as a result, at the very cloud top, we're talking about meter to 30 meter range, and there's a net loss of energy at the cloud top. So if you have a net loss of energy, what's going to happen? It's going to cool. So if you have the air, it's top heavy because it's colder, and what happens is it generates turbulence. So the turbulence you see when you are under the stratocumulus cloud is mainly generated by what we call the infrared radiative cooling at the very top. So that generates the turbulence here. And so this, in addition to that, and we also have, the moisture supply from the ocean, and it's always there. That's important because that determines how long this cloud is going to stay there. Okay? And because you also have the so-called entrainment process. Now you have all this quiet air above, and then you have all these turbulence eddies in the boundary layer. What's going to happen is all these eddies is going to scoop some air from above and incorporate that into part of the boundary layer. As a result, your boundary layer has a volume increase, and guess what? Your boundary layer height is increasing. That's why, with this constant pushing from the larger scale, substance, and it's not pressing the whole boundary layer to the bare surface because we have this turbulence, entrainment going on. And so this is a picture of the entrainment in the clear air, and it's basically, in simple words, it's just, you scoop some air from above into part of your boundary layer, because if you have turbulent motion. And when you have cloud, this is harder to deal with, and this is part of my thesis research, when I did my PhD, and I continue to work on that for many years after. So when you have a cloud, and then your source of turbulence is up above, but this is where you bring the dry air into your boundary layer as well. So it becomes a lot more sophisticated than in the clear boundary layer. So lots of research are going on in there. So what's the significance of a boundary layer cloud? In the past 30 years also, the National Science Foundation and also the Office of Naval Research, and also DoD has put in lots of money into studying the low-level cloud, like stratocumulus cloud, and which is good for us. That means funding. And so now, and lots of those were driven by climate change issues. Now, this was the research from back in 1984. So they found now these low-level cloud, if the percentage increased by 4%, which is easily getting there, and then it's enough to offset the effects of doubling the CO2 for global warming. So these clouds, they have a cooling effect for the climate. Now, why? Because these clouds are low, so the cloud temperature are not too different from the ocean surface temperature. So in terms of outgoing radiation, it's about the same, as you don't have cloud. But if you're looking into the solar radiation and how much the Earth system is going to get, these clouds are much more reflective than the ocean surface. So as a result, we are not losing as much of the infrared radiation, but we're getting much less, solar radiation. So as a result, climate-wise, it has a cooling effect. So that's the drive for many of the past research on stratocumulus cloud. Now, the Navy and lots of and DoD also have an interest in the effects of aerosol on the cloud microphysics. Now, so what you see here is if you have a ship plume, and then so that means now you have lots of small particles that the water vapor can condense on. So as a result, you generate lots of little cloud droplets, but then the amount of water vapor is about the same. So you have lots of them competing for the same amount of water vapor. So as a result, you have the cloud droplets are smaller when you have lots of aerosol. So what happens is, so when they're smaller, and then they're more reflective. So that's why you see all these ship tracks. Okay? So you can imagine, how this can be used by the Navy. Now, one of my colleagues, working on satellite remote sensing, and he has some clarified research, and basically to figure out, from measurement of these ship plumes, what they call ship track, and so they can try to figure out, what kind of aerosol and the amount of aerosol, and they figure out what kind of fuel and generate those type of aerosol, and then you can figure out what type of ship is under there. And so now, because when you have the cloud cover, and then all your surveillance cannot go through the cloud in the visible part, and then you have to figure out something in that. So that's very interesting. So now, those so much for the basics of boundary layer and surface layer, air-sea interaction. And so I want to introduce my recent research programs in air-sea interaction. Now, this one, many of you probably heard about, and this is Office of Naval Research MURI program. It's a multidisciplinary University Research Initiative, MURI. And so I put in a proposal with 5 other university PIs together. It's a group proposal, and we were lucky to get funded. And this is called the Coupled Air-Sea Processes and EM Ducting Research, or CASPER. And so, and then this is a 5-year project. And so this has lots of collaborators, and including PIs from different universities and postdocs and graduate students, and we keep getting collaborators, because lots of people were interested, and so it grew to about 90 people. This is a slide I borrowed from the recent review at ONR. So it's very multidisciplinary, because I have people from the oceanographer, and this is mechanical engineering, and I have people, this is mechanical engineering, and there's a civil engineer, this guy from civil engineering, and then there is some government, double E here, and this is oceanographer, and geez, not too many meteorologists here. I just realized that. So anyway, it's a very truly multidisciplinary team here. And some of those are my students there. So now, what are we dealing with? So we talk about gradients in the atmosphere in temperature and humidity. Okay. Now, so this project has to do with when you have a radar, okay, and you want to send the beams to whatever you want to detect, but you may not get there. And why? Because the atmosphere is in the way. Now, when is it in the way? Okay, and it's quantified by this quantity called modified index of refraction. And you can see it has to do with the pressure, and it has to do with temperature. And this E is the water vapor pressure. It's the amount of water vapor. And there are different regimes, and some of them we're less concerned, some of them we're more concerned. So think about this. This is the Earth's surface. And so in this situation, when the dm/dz, the vertical gradient of this modified index of refraction, is less than 0, so the beam comes out and is going to bend towards the Earth. Now, so you see this term has the Earth's radius in here, so we can see it easily. So this quantity, it bends towards the Earth. That means trapping. So it's going to come to the surface, bounce by the surface, and then go again. So this means you send the beam from here, and you can see this, you can hear this from way, long distance, from here. And so, way beyond the line of sight. Okay. Now, in there are situations that you have, send a beam is going that way, okay, and this is for the standard atmosphere. Now, so what's important here is you want to find this trapping layer where dm/dz is less than 0. The gradient is negative. Okay. Now, in this whole formulation, the gradient is very sensitive to the water vapor, so we really need to nail down the water vapor amount. And so now you can see, where do we have the gradient in the boundary layer? One is near the surface, okay, and this one is labeled right, so they should go this way. Okay, specific humidity and temperature, and then also at the top of the boundary layer, because now you need to move to the dry atmosphere and the warm atmosphere, so you have the gradient. So this is where we normally have a duct, and then we call it the evaporation duct. And this is another layer with the negative gradient, and we call this the elevated duct. So moisture gradient is the most important. And this is a picture about the surface, different type of duct, and this is the surface duct. So the trapping layer is at the surface. So if your radar is here, okay, and then from far away, and you can still hear the signal, you can get the signal. But if you have a low flyer that's just above this layer, and then you wouldn't be able to hear it. Okay, so my student was telling me, the stories about them on the ship. So they were trying to, they can hear the other ship, but then there is a UAV there. They couldn't hear it, and the commander of the ship was really mad. So what are you telling me? I can't hear them, and how come I can't hear this guy? And so they pull out this, and this is why. So, now in the situation like this, is a surface-based duct. Now you can see the trapping layers here. Now, so there are regions at the surface you have concentrated energy, and there are regions there's none. So there are lots of spatial variability in this. So you would not, this is what they call the skip zone. And now if you have this totally elevated duct, and then if you are inside here, and again, you can hear from far away, or be heard from far away, or, and if you are here and you are in that radio hole. So, so that's why the Navy is interested. And this also has the commercial implication too, because, all the communications nowadays. And the Navy now, why they fund this project? Because nowadays, everything, it depends on what they call the EM spectra. Okay? And so everything is communication, and they don't do anything, not too much on the ship locally. So everything depends on communication. So if you want to kill the enemy, the first thing you do is to kill their communication. So there are lots of engineering in these. We are just understanding the environment. See, we're kind of passive. Understand the environment, see how they affect the Navy operation. But there are also other side of the research, and they try to jam. So they create some false signals, and like using a swarm of UAVs or wave gliders. So and if so send out EM signal from there, so the enemy may think the signal, the fleet is right there, but it's actually 1,000 kilometers away. And they can also jam and send different false signals. So there are lots of things that I don't really understand in there. Now this is not a new issue. Back in 1944, and you can see here, and then they notice, when they look into the beam, the propagation here, measure the propagation, they notice, when you have very low inversion height, that's where that trapping layer is low, and then they can get high signal. So you see this very nice correlation. This was back in 1944. So in the old days, this has been an old Navy issue, and but nowadays, because this has so much, underneath, it has so much of the air-sea interaction component to it in the basics research. So this now has become like a meteorology community, and we are interested in this. So not just the Navy presence. And this is the very subtle thing. It's a difficult problem, as you can see here. Now I have two profiles of the M profile, the M. And so now these two give the same, the so-called evaporation duct height, but their shape are a little bit different. But then you can see now, so this is the propagation factor, and think about this as propagation loss. The lower it is, it's more loss. So you can see how different these two are. So but if you just eyeball these two profiles, they're not that different. Okay? So this is the a subtle variation. It makes a big difference in the propagation, and so that's what makes it interesting, as also what makes it very important, and very hard to do. So that's why I'm trying to use the small boats to get to the close to the surface, and without any flow distortion by the ships. Okay, I don't like the big boats because there is a boat in the way, and so they disrupt the very atmosphere that I want to measure. So the small boat, work magic on that. So now the question is, can we predict that accurately? Now, in the past, forecasting is more on the sensible weather, temperature, humidity, wind, precipitation. And so the grid scales, as I mentioned, is kilometer range. But all these, what I'm working with, are the very small scale. Okay? So are we equipped to do that? Not really. So, and even, how we should evaluate the model performance, it's a different story, because now we're looking in the gradient. Just to give you a little feel of this is from one of my students' work. So when we do this is from the sounding, And so we just with balloon sounding, and we get the data. And this is from the Navy's coupled model, the operational forecast. And you can see, nowadays, forecasting-wise, we're doing a pretty good job. It's mostly on this one-on-one, around that. So statistically, it's a good job. And for a specific day, it may be, larger deviations. And so this is for, so think about this as temperature, as some other temperature that we normally use. And this is the amount of water vapor and the wind. And then you look into the that M quantity. And if you look at just the M, it's not too bad. Sea surface temperature, is actually one of the most the hardest thing to get accurately. And we've been struggle a lot with getting correct sea surface temperature. But overall, it's okay. So these are some mean statistics and for this particular project. And now, if we are looking into the profiles where we want to identify the ducting layer, so now you can see this is what the model says, this is what the sounding says. Now, so this is where that gradient is, and now the sounding shows, the measurement shows the gradient here. Now, so you look at the M from the model, and this is where you have that trapping layer, and from the observation, you have two of them. This is one trapping layer, this is two trapping layer. So when you compare the trapping layers and the ducting layers, now the blue is the blue is the, I forgot, blue is the sounding, and red is the the Cohen model. And now you can see huge differences, in the gradient, because now we're looking into the gradient. And then we can say, well, your sounding has much higher, vertical resolution. So how about we subsample our sounding into the same resolution as the forecast model? You still see a significant large deviations there. So that means, the forecasting is, for specifically for this application needs lots of improvement. And that's the whole motivation behind, supporting CASPER. Now, this is my new project that I just learned. I'm funded. And so this has to do with the atmospheric effect on the propagation of the optical wavelengths, much shorter wavelengths. So the issue here, it has to do with the laser. So you probably heard about high energy laser weapons. So now, now there are atmosphere in there, and so what's the boundary layer, and that's turbulent. Now, so when you have the turbulence, this is the perfect wave coming from the laser source and going through the atmosphere, and you can see this distortion of the phase. Now, what happens is with this turbulence in between, now when it gets to the target, and it loses its focus, and that means the energy per unit area is getting much less. So, so the ability to kill is much less. And there's also an issue is going through the atmosphere, and there's attenuation. So this effect of the turbulence is called scintillation. Now, so on a hot day, if you drive, and then you can see the air in front of you, so that's the effect of scintillation. And this is more affected by the temperature and, in turbulence, in the small scale turbulence range. Then the attenuation has to do with the absorption of the atmospheric gases, and then there's also scattering, and there's also aerosol. Normally, now we consider the gas absorption for the solar radiation in the atmosphere is pretty small. So, and for some applications, it's very important. But if you do the energy budget, that's pretty small. Now, this is different when you have a laser source, because now you have a huge source. So this absorption is going to be large, and large to the extent along the path it can heat up the atmosphere and generate local turbulence, and then these turbulence will go like this, and so downwind, and so you will see this laser beam kind of deviate towards downwind. And I learned that the first time the first time I learned about that, it was very fascinating to me. It's called thermal blooming, which I never thought about. So so there are lots of new issues in this, but all have to do with atmospheric turbulence. So my project title is called Quantifying and Understanding Environmental Turbulence Affecting Lasers. So one of my colleagues suggested, oh, you can make it into Catal, and which means what's up. So I like, okay, I wouldn't be able to come up with the fancy name, but oh well, that's good. And maybe that's the name that got me funded. So yeah. So anyway, yeah. So what do we deal with? What are the issues in air-sea interaction? Okay. Now, so Number one is the ocean surface is not homogeneous. And so it appears homogeneous, okay? Now, but it's actually not. And this is from some aircraft measurement we did, offshore here. And so you can see now along the path we can measure the sea surface temperature, and you can see how much variation there is. And on a day-to-day basis, there's also lots of variation. Okay? So now why do we care about this? And because the one basic theory that we've been using again and again is called the Morning optical similarity theory, and you don't have to remember that. And its basic assumption is it's all horizontally homogeneous. And so, but we don't know if you have a surface that's not homogeneous, what's going to happen. And also we don't know at what point this inhomogeneity will kick in and it become invalid. So these are all the questions that we don't know. So if you look into what's happening here, now so when you have this gradient in temperature, okay, now this is the sea surface temperature. So you see there's a sharp jump of 16 here, so this is like 13, so 3 degrees. And this is within a very short distance. And so you see it's turbulent here, and you can see it's so obvious. And then it's less turbulent here, when you get into the cold water region. And if you look into the fluxes, the coupler that I talk about, so you can see how much momentum, this is sensible heat flux, it's positive and 10, and now when you get to the other region, it's negative. So this means that you get heat from the ocean, and here it means you input heat to the ocean. Okay? So you are looking into very different air-sea interaction process around here. And so that's why we're interested. Now, the cloud and everything that's happening in the atmosphere, like the boundary layer cloud or precipitation, and that introduces spatial inhomogeneity as well. So you can see here, this is from one of the thesis study as well. So the fluxes just varies, from this end, to that end, and corresponding to these convection and no convection region. So atmospheric phenomenon itself introduced the inhomogeneity in this. And another issue we need to study is the waves. Okay? Now, particularly for this EM propagation. So now, normally we say the wind is driving the waves as the wind wave, right? So now, when we have very low wind and then we have strong swell, and that's the case, the swell is going to push the wind. That's when we have momentum coming from the ocean to the atmosphere. And now, if you look into the measurement from my small buoy, now in those situations, now normally we have like a wind speed increasing with height, but in these situations, you can see the wind speed increase and then it decrease with height. Okay? And the temperature gradient, it's very different here in these three situations. So we need to understand what are the effects of the waves. And also that Morning optical similarity theory, and we call it MOST, and that theory, and it was developed over land. There's no waves over land. And now we have a moving surface that's responsive to what's going on in the atmosphere. We're really talking about air-sea interaction. So then what's the outcome of this interaction? How is it going to affect this profile? And these are the basic science questions that we need to answer. And so because of the stochastic nature of turbulence, okay, and we don't have a good theory, and it varies all the time. So boundary research has been heavily relying on measurement. So that's why I'm out into the sea or on the airplane, I'm just traveling to do all kinds of field work, and that's the nature of boundary research. So I want to talk a little bit about measurement capability. Now we use these different capabilities tailored to different field programs. This is what we use in CASPER East platform. So now we have 2 airplanes. Now this one, you can see it has a drone, it's fully instrumented. And so this is operated from off Marina here. by the Center for Interdisciplinary Remote Piloted Aircraft Study, SURPASS. And so this drone is fully instrumented. Now, so this aircraft, the manned aircraft, the lowest level we can fly by regulation is 100 feet. And we do that quite a lot, 100 feet. When you're on the airplane the first time, it's a bit scary. All of a sudden you realize you can see fish. So, but that's not low enough for us. We want to be really low. And what do we do? So this drone was developed so it can be reeled up and down. And so we can, so we get measurement from 2 levels, or we can just use this to go up and down. And this one can go down to 30 feet, which is 10 meters, which is so much better than 100 feet. So, and then this aircraft has lots of the remote sensing capability. It measures the surface waves, measures the surface temperature, and so it gives us a larger area survey of the ocean. And then we have 2 ships involved, and then we have all these small platforms. And so this is the ocean wave glider. I have another project working on instrumentation for the wave glider, and you recognize the small boat and tether balloons. And then we have these small buoy. So you see, for these, I'm going small. Why? Because I don't want flow distortion. And I don't want the thermal heating effect by the platform itself. So we're going really small. And this one, when Alex and the folks doing it, I asked them to get the sounds, all the way to push it to the surface and then release it, because the lowest few meter is very important. That's where we have this sharp gradient. And and we also use the pier, and this is a 500-meter pier at Duct, North Carolina. It goes all the way in the water. And there are some underwater gliders. Now, so this is the in the Quintel in this new project, and now we are focusing on the optical turbulence. So we're using some land towers, and we have 2 field camping. We're going to do over the water one and another one over land. Oh, you recognize this is Holly doing the balloon launch from last year. And and we would like to use the small balloon and the John Martin mast, the ship mast, for turbulence measurement. And so we have different levels of mast, small ones. You see this, I believe this is the one at the aquaculture lab. And or the more beefy ones, this go up to 52 feet. And then we have much larger tether balloon on this mooring system. There's a truck for it, and this one we can go up to like a 500 meter. So it goes a lot higher, have a much larger payload. And and we try to develop measurement capabilities and as needed. As you can see, the evolution of this small boat. This is the Moss Landing rib. So how we evolved from the initial, the initial concept in April 2015, and then to October 2015. And so here we have the manual reel. And then, this mast is kind of a small, just proof of concept measurement. And then when we get to CASPER East, and we realize, this is lots of manual work, so we really need manpower on that one. And then, so we turn it into, actually Ryan, my instrument engineer, turn this into electric reel, and that makes it so much easier. And then we came back, last year, and we need to do more, and we get back to the rib, and then you can see now this mass is much more hefty than our humble beginning at the early, a year before. So this is how we are trying to perfect our measurement, step by step. I think Alex knows every step of this. So. Yeah. Okay. So now in the field program with all these different things, and then we need lots of coordination, and we want coordinated measurement. So this is, you can see all the dance that this is our orchestra that we need to conduct during the field program. So we have multiple ships, when the ship is going where, which direction, and so for the EM link measurement and the link between the ship and shore, and ship and the aircraft, and this ship is in the middle doing the environmental measurement, and also we have these coordinated radio sound launch, and we see at certain time, and then boom, the shore, this ship and this ship, we're launching radio sound at the same time. That way we have the concurrent measurement, of the atmosphere, and this is a different type of evolution. Now, and so this is a ship to ship, and this one here, let me see if I can get this to play. Does it? No. Okay, so this shows, the propagation measurement is on a day-to-day basis, and this is supposed to be a video. It can go like, from different frequencies, and this is for a lower frequency, this is a higher frequency, so you can see what we did in collecting this EM signal. So the idea is we collect all these EM signal, and we also collect the environmental measurement, at the same time, so we know what's going on in the atmosphere that result in these EM signal. And this is what's going to happen in CASPER West, and that's going to be offshore of Point Mugu. And so in this project, we're going to have this guy. It's a flip, so this is a ship when it's in transit, and when it's on station, it's going to flip like this. So we use it as a stabilized platform. It's very stabilized. And then, it has long arms. It's now going this way now. It has long arms to get into the water, so we don't have flow distortion. And that's what we need, for measurement. And then again, we need to coordinate, and we have this new boat, new ship, Sally Ride, is going to go in between here. The surface side will be here, and then we need to make plans about all the EM links, so you can see all these. So this time we're doing it differently. We want to measure lots of the fixed distance link and in different wavelengths, and then we also have the range-dependent links. So there is going to be lots of orchestra playing in this coordination as well. Now, so in Cadell, and so it's a different game, and this is for the optical and laser. And so this one is planned, at the landing facility at Kennedy Space Center. So we have this 5-kilometer long landing pass, and it's all corrected for Earth's curvature and everything. And and we want to put in the mobile systems, that for laser. And then we want to put, measure the atmosphere properties along the path, and then, use my tether balloon and go up, down, and then for the turbulence measurement, and hopefully to use my small UAV. That's another project we're trying to develop, using those toy like UAVs, from the hobby market, and they're like only $200 a piece, so we don't care about losing them. And then it's like radio sound, but it has some reusability. So we try to instrument these for turbulence measurement. If not turbulence, at least we want to do the high rate temperature measurement, so we can, that can help to support this high energy laser project. And what do we do with these data? Okay, we better do something. Oh, this doesn't come out well. This is CN square. Square should be on top. So now we have the measurement, and so this is like the plan, for this one. So measurement on one side, and we also have this very fine scale model. Its resolution is like a 20-meter or 5-meter resolution. It's called large eddy simulation model. They are trying to resolve the turbulence in the atmosphere, and of course, if they have such a high resolution, they cannot cover a large area. So its only domain is probably 2 kilometer-ish, but that helps us to understand the physical processes in the boundary layer. So we use that as data. So we have the measurement of turbulent perturbations and optical measurement, the laser measurement, and then we put into this is the key variable we need to look into for scintillation. And then we have, the other measure, the meteorological measurement, and it can go into these models, and then we can see what comes from the model, And then there's also the mesoscale model, the forecast model, and eventually we all come together to see how we can do the CN square better. So that's basically the purpose of making measurement in this. And so now, and this is the measurement we did from the yo-yoing on the small boat of Mouse Landing Rib, or the work boat in CASPER East. So now I asked for 7 up and downs each time. So this is what you see. Why do I want to make 7, or more? because it's a stochastic process. Every time you're going to measure something differently. Okay? So I cannot rely on just measurement from one, because it's just one realization out of many happenings in this stochastic process. So I need many, and then want to get the mean. So you can see this green, the red line is actually the mean. It's a polynomial fit. And then the green is a model. That the one that I said most, the Monty-Opkoff similarity theory. And so you can see in some cases, hey, the theory works pretty well, so we're all happy. But then you can see other cases, now the theory does not work very well. And in these cases, it happened to be, if you can see, the air-sea temperature difference is small, negative or positive, and then that's when the theory seems okay. Now, when this quantity becomes larger, and that's when, especially this one, this is the so-called stable condition. This is the exact condition I was trying to catch in the Santa Ana project, because when you have the warm and dry air comes in, and so you create the stable condition, and then you can see the significant difference in there. And so we use this, and we can derive for the first time the measured evaporation duct height, directly measured, and then we can compare with the model, which is this one, the core, and then we can look into have a good evaluation of how the model is doing. And then we also, to look into some theoretical study to look into the differences and, how this difference, related to other quantities in the atmosphere. For example, the low-level water vapor difference versus at the sea surface temperature, at the sea surface. So we do some of these analysis. So, so we're not just collecting and leave it, somewhere. So we've been working with it. Come to the summary here. Air-sea interaction and atmospheric boundary are essential aspects of meteorological research. So the meteorological research is not just forecast. There are lots of things going behind the forecast, and to improve the physical parameterization. I'm sure in your field of research is similar. Okay, so improve the physical parameterizations and how we can forecast this thing better. And now we need to deal with, in the boundary layer research, the stochastic processes associated with geophysical turbulence and how they are related to the larger scale atmospheric and ocean forcing. Because after all, it's what's going on in the surface is changing, what's going on in the atmosphere. So we want to make that connection. And boundary low-level clouds and fog are a significant part of the marine atmospheric boundary study. So I will continue with on that, and we'll work with Kenneth on that as well. Air-sea interaction and has lots of important applications to civilian and military use. So for example, for the EM propagation and for we call this EO, electro-optical propagation. And so now my major problem now is I need to deal with the work with the heterogeneity of the surface and non-stationary, which is along the same line, and spatial, horizontal inhomogeneity and temporal variability, and also we need to deal with surface waves. And so our study are heavily rely on measurement, so we need to develop these capability as much as we can. And this is a field of truly multidisciplinary research, and so we need to involve lots of people from other different areas. And finally, I have my big thank you to Moss Landing for supporting my research. So I have a list of JD, Jackson, Alex, and they work really hard on the ship to get what we want. And they are the best crew, from all my experience, because they don't mind to go extra miles to get what we want. And I think JD is even part of the science team. Sometimes I forget about stuff, and he will come to me and he will say, "Hey, Qing, don't you want to do that?" I was like, "Oh yeah, right. Oh, okay, I forgot about that." So that was really good. So be careful. We are turning him into a meteorologist. So and then Kenneth, of course, help, and so we are doing collaborative research, and Jim, for all the administrative support, and most importantly, the students. These students, you are so helpful. I'm really grateful to what you have been doing for my research projects, and I hope you had fun too. And I'm hoping to involve you more, in the future. So I can see I'm not short of field programs. So if you like to get onto the sea, or sometime maybe get on the plane, so that's also possible. So yeah, if you are interested or have any questions about meteorology, general meteorology, so I'm still a meteorologist, even though I have the boundary in there. Okay, and so feel free to email me, ask questions. So yeah, so hope to enjoy the seminar. All right, thank you very much.
Do we have any questions?
I do.
Yes, okay.
In your last slide from I think the CASPER project, you showed that the ducting height was fairly small. It's on the order of 6 meters or so. And so what's the extent? What's the range of the duct?
Okay.
The lower duct.
The duct ranges from like a meter to anywhere 30 meter,
Yeah.
but most frequently we see 10 meter. Now here when we make the measurement, and we're looking at like 4 meters, 6 meter, and so that's a bit too low, because I want it higher, and that's why we're moving to we're going to Southern California, where we have the higher sea surface temperature, and that gives us a higher duct. And so yeah, I would love it, if the conditions here is right, that can save me so much heartburns, going to Southern California. Yeah.
And so there must be a relationship between the height of the duct and the propagation of the wave, or the wavelengths of the
Yes.
of the electromagnetic signal.
Right.
that propagate.
Yeah, exactly. There is a direct relationship, so formulation you can calculate. Like a certain duct height is going to trap certain wavelengths, and some other wavelengths don't care. Okay? So there is a formulation for that.
Okay. And so that's got to relate to aspects of the mirage that you see
Uh-huh.
right along the sea surface. Is that because those signals will be propagated differentially along
Mhm.
that?
I think it might be related. Now, however, the mirage is more of an optical phenomena, and the ducting is more in the radio waves, the longer wavelengths.
So X-band,
Yeah.
right?
X-band, C-band, S-band, so even L-band, so, but nowadays there are more interest into the higher wave, the higher frequency one, go into the K-band. I think there are some, some classified research in that. So in my project, the program manager always want to put like a trailer in there, and so we don't know what's going on. So there's a trailer there. Yeah. So there are some frequencies of interest. Yeah. The higher the frequency, the harder it is to make measurement.
And you also talked about the communications aspect, and those are typically in the 2 meter wavelengths.
Mhm.
And 2 to sometimes 4 meters in terms of radio frequencies. Are these wavelengths being affected by this type of
I think it depends on the wave, the duct height. So I don't know exactly, for certain wavelengths, but I remember, I think in the old days when they started, it's all for the lower frequency, and it's only nowadays it's getting higher and higher.
Well, my first question is, when you showed those aircraft measurements of temperature, and you saw those striking all those striking variations, how big were those, and what do you think is driving that small scale?
Well, those if we're talking about gradient, it varies quite a lot. Now, what I realized, in doing like my students working on like coupled air sea, coupled model, forecast model, I realized the ocean, it's the diffusivity is so small, so it's the mixing, the time scale for mixing takes a long time. So, so the gradient, very often you see really sharp gradient, and simply because there's just not much horizontal mixing. Unlike in the atmosphere, you have something, warm air and cold air here, and very quickly they mix out. But in the ocean, this process is very slow. Now, when we were in CASPER East, and off by the Gulf Stream, and so there was one day, we have this gradient, like 2 degrees within, I don't know, meters. So I thought my sensor was wrong. I look at my sensor, it's going like that. And then so I said, oh, this is not right, and so I went to the ship flow through, and I see the same thing, so it was amazing, so this happens more often than not, so I think it may have to do with the ocean diffusivity, but I'm no oceanographer, so I think we do have an oceanographer on board, and he's very interested in getting answers to these. So Kip Shearman from Oregon State, I don't know if you know him, but he's pretty good in these things.
I was just going to ask, you mentioned that in the forecasting models, the SST is one of the hardest parameters to forecast. Are the sources of the errors in those forecasts relatively well understood, or is it completely unknown?
No, that's a very good question. Now, it's not only hard to forecast, it's also hard to validate, okay? Because it's very difficult to measure it accurately. Now, so what happens is at the ocean surface, at the very top surface, it's like at the cloud top. So, so the ocean surface is emitting more infrared radiation than what it's getting. So there is a cool layer, at the very top of the layer is less than centimeter, maybe millimeter or less, and that's cool. And so it is this cool surface, that's where the atmosphere feels. So we need to measure that surface. So imagine all the ship flow through data, it's way 2 meter, 1 meter. So we're not getting that. And then if you stick a thermometer in the water, you're also not getting that. And not to mention you have the waves and stuff, it's in there. So we want to use these radiometric method, so basically measure the radiation. But you are always some distance away from the surface, like on a ship, and then there's lots of water vapor in between. So you need to somehow get rid of those water vapor effects. And in addition, you also have the reflectance from the sky, getting into your camera. So on the into your lens. So now my new gadget is called the ROSAR. So that's it's a calibrated sensor. So it basically is looking at the sea surface, and then it has a mirror to turn, let it look into looking at the sea surface and look into the sky. So for the sky correction, and then it look back into 2 black body source, and so that way it's calibrated. So we get the calibrated sea surface temperature. Now I only get this from for CASPER East. I didn't have this before. So so now it's a must-have for my project, because that's the only way I know, what's the sea surface temperature. And we have gone through in the CASPER analysis meeting, gone through so many times about exactly what is the sea surface temperature, because the other ship don't have my gadget, so we're trying to find the time when that ship is close to where we are, and then make the connection, and then try to do the correction. And we call it the cool skin and warm layer correction. The cool skin is that very top for infrared, and there's also this warm layer because of the solar radiation absorption of the top water. So these all, because now when your flow, you want to use the flow through, and then that may be below, or in that warm layer. So we need to make that correction using some mixed layer assumption. So there are some models for that. Yeah, that's a super good question.
Well, not, thank you for.
Well, Alex,
The Oregon State AUVs, was there any interesting information that came out of that? Because I know they were, we were going on the back and forth on the track. They were deployed. I was wondering if anything interesting.
the AV.
AUVs, or the two, the torpedo with fins. the Oregon State AUVs that they had back east. I think they were deploying them.
Oh, you mean the the ocean gliders?
Yeah.
Oh, okay. Well, they got some good data, but they can only go up to, not to the sea surface, and so you do get the profile. So they go like up and down and up and down, for the whole month in there. You get lots of data, about the ocean and also about the wall, of the gradients and all that. So they can use that, and I think KIP is doing something about it. Yeah, ocean is just a bit too wet for me.
That's it. So thank you very much.
Well, thank you.